Hi everybody, thanks for joining. My name is Adam, and today we're going to talk about combinations and permutations for the GMAT exam. Now, this video will be helpful to you for, to various people for various different reasons. Number one, if you're the type of person who really has no idea where to even begin with combinations and permutations questions, or if you don't even know what I'm talking about when I say combinations and permutations questions, we'll see examples in a moment, this video is definitely right for you. Also, if you're somebody who generally knows what I'm talking about within combinations and permutations, but only relies on formulas to solve these types of problems, then this video is also probably a good idea for you. What we're going to be talking about in combinations and permutations is really situations in which we're going to move away from formulas and more into a broad and intimate understanding of the concepts behind things. Because after all, on the GMAT, it's really the concepts that count and not the formulas. So even if you have no experience with this stuff at all, and don't even know what I mean when I say a combinations and permutations question, that's absolutely fine, and this video is right for you. Now, we're going to be working through this through the worksheet, um, which you can actually find a PDF of right beneath this video. So there's a worksheet, and then there's a question set right afterward, and we'll be going through both the worksheet together, learning the concepts, and then the question set afterward. So, before I get started, I want to talk about two very important concepts in uh, combinations and permutations. And these are two concepts that are almost so basic, they seem very intuitive, and they seem like some of the most basic things that you can ever come across in mathematics. These are going to be the underlying concepts of what we're going to be talking about today. So concept number one, let me write this right here, is called the multiplication rule. Multiplication rule. Didn't write that very well, but you get the picture. Multiplication rule. And concept number two is happily going to be called the addition rule. Now, these are going to be our starting points. So we're going to take a moment to take a look at both of these rules right now. So let's start by looking at the multiplication rule. Here it goes. We're going to start with a question, a very basic question that you could probably answer in no time if you just thought about it conceptually. So inside a closet, there are 4 shirts and 3 pairs of pants. How many outfits can be made containing 1 shirt and 1 pair of pants? Well, I'll give you a moment to think about it, but your moment's probably up. You've probably come to the realization that, well, if I just multiplied the number of shirts, right, 4, by the number of pairs of pants, there are 3 of those, I would get the number of outfits that contain 1 pair of shirts and 1 pair of pants. I got the number 12. So this is called the multiplication rule because I took the number of shirts right here and I multiplied it by the number of pants right here. Now let's take a look at the addition principle. We're going to come back to this in a second, and you're probably wondering why it's important, and I'll explain that in a moment. But let's take a look at the addition rule. So similar question. Inside a closet, there are 4 shirts and 3 pairs of pants. How many outfits can be formed containing either 1 shirt or 1 pair of pants? Well, once again, I'll let you think about it for just a brief minute. Now, even in that time, you probably figured it out. Okay, you probably thought to yourself, well, if I'm taking 1 shirt, I can't take anything else. So for any shirt, I just got 4 of them. That's going to be 4 shirts. And if I'm taking a pair of pants, I can't take anything else. So that's just going to be 3 of those. So 4 plus 3, that's going to give me 7, right? So there's 7 outfits that contain either 1 shirt or 1 pair of pants from the shirts and pants in this closet. All right, so let's go back now. Let's think about some of the differences between these two rules. Now, the biggest difference between the addition rule and the multiplication rule is that when I'm dealing with the addition rule, I'm dealing with the word or, right? I'm doing one thing or another thing. When I'm dealing with the multiplication rule, I'm dealing with the word and, right? Doing one thing and another thing. Let's go back to the very first slide here. So the multiplication rule, if simply put, it says that if I'm doing one thing and another thing, that means that I multiply the two things together. The addition rule, if I'm doing one thing or another thing, well, that means that I add them together. So and is multiplication, or is addition, and it's a good idea, especially when we get into more difficult, more conceptually challenging problems, to come back to these very basic ones, right? Just come back to that closet. Think about that closet, right? Those 4 shirts and those 3 pairs of pants. Or think about that closet, either one shirt or one pair of pants. And combinatorics will really start to make a lot of sense very quickly to you. All right, now that we've got that out of the way, let's go to an actual combinatorics question. So this is going to be question number 1 from the worksheet. So question number 1. In how many different ways can 3 of the 5 letters A, B, C, D, and E be arranged if no letter is repeated? Okay, well, let's think about this one for a second. Let's first of all give ourselves some examples of what this question is asking about. Okay, so we want to find the number of arrangements of 3 of these letters. So one arrangement might be A, B, C. That's one arrangement right there. Another arrangement might be, I don't know, B, D, A, right? That's another arrangement. Another arrangement might be D, A, B. There's another one. All right, and I guess if I just kept on counting, eventually I'd figure out that I can't find any more. But the question here is, well, how many would that be? How many are there in total? How many are possible? Okay, well, what we're gonna do is approach this using our addition rule and multiplication rule, so that you really get a good grip on how this type of thing works. So first of all, I'm choosing 3 letters, right? Because I'm choosing 3 of these 5 letters, so I'm choosing 3 of them. So I'm going to choose one letter and another letter and another letter, right? And remember, I multiply them together because each time I'm choosing one and another, one and another. Make sense? Based on that multiplication rule. All right, now I'm going to think to myself, okay, how many different letters can I choose for the first spot? How many different letters could I choose there? Well, I could choose any of these 5 letters. So that's going to be 5. So I can put a 5 there. I can choose any of those 5 letters. Perfect. For the second spot, once I've chosen the first letter, how many letters are left that I could choose? Well, I can choose anything except for the letter that I chose in the first spot. So I can't choose the first letter that I chose because I can't repeat any letters. So I can choose anything else. So that means that there are going to be 4 letters left. Now once I've chosen the first 2 letters, now I'm going to figure out how many letters I have left to put in the third spot. So I can choose any of the letters, any of those 5 letters, except for the 2 that I've already chosen because I can't repeat any letters. So there are going to be 3 to put in that third spot. And I multiply them all together. 5 times 4 is 20, times 3 is 60. So the answer here, well, there are going to be 60 of those arrangements of 3 letters. So if I just kept on counting here, I would have to write down 60 different arrangements before I figured out that I couldn't write any more. So the total possible number is 60. All right, now what we did right here, I'm going to give it kind of a name. Um, you can call it whatever you want, but I like to call this the slots method. Call it the slots method. Right there, the slots method. Basically, I'm saying how many things can go into this slot right here, and the answer would be 5. How many things can go into this slot right here? The answer is 4. And how many things can go into this slot right here? The answer is 3. So that's why I call it the slots method, and it's something that we're going to be returning to quite a lot today in talking about combinatorics. Let's go to our second question. So question number 2. In how many different ways can 3 people from a group of 5 married couples be arranged if no 2 people of the 3 may be married to each other? All right, now I'll invite you to take a moment to try to solve this one on your own using the slots method, using everything that we just did. Now, so I recommend that you kind of pause the video and try to solve it on your own. In a moment, we'll discuss it together. Okay, so hopefully you had a moment to look at this one on your own, pausing the video. And if you found something that you're very confident of, perfect. We'll see if you're right. If not, that's okay. We're looking at it together. Learning can be a slow process, of course. So, let's first of all try to figure out what this question is really asking us and what some of the constraints are. It says, in how many different ways can 3 people from a group of 5 married couples, okay, so we're choosing 3 people from a group of 5 married couples. Let's write that. So we're choosing 3 people from a group of 5 married couples. Well, 5 married couples, that's going to be 10 people in all. That seems like it's going to be important somewhere. So we've got 3 people from 10 people. But here we don't want any 2 people of the 3 to be married to each other. So in other words, of these 3 people, we don't have a couple among this group of 3 people that we're choosing, right? So we can't have a couple. We can't have 2 people that are married to each other in any of these 3-person arrangements. All right, so this might be tricky with this little constraint, but let's at least start it in the same way that we did the previous problem using the slots method. Here we're choosing 3 people, 1 person, and another person, and another person, right? And we put the and because it's the multiplication principle once again. So we're choosing 1 and another and another. For the first person that we choose, well, we could choose anybody, it seems. So any of these 10 people. There are 10 people in all. So we'll put a big 10 there. You could choose any of those 10 people. Now, once we've chosen that first person, we're going to think, how many people left are there to choose for the second spot? Well, we could choose anybody except for, of course, the person that I've already chosen, because I can't have the same person twice in a group. I want 3 different people. So I can choose anybody except for the first person that I chose. But I can't choose that person's partner, their spouse, their wife or husband. So I can't, let me write that, I can't choose this person's partner. Oops, I know that's not very clear. I can't choose this person's partner right there. So I can choose anybody except for this person or this person's partner. So anybody except for the first person or the first person's partner. So that means that of those 10 people, there are 2 that I can't choose right now when I get to the second slot. So I've only got 8 who I can choose. All right, now I'm going to get to the last slot. Now remember, I've already chosen 2 people, so I can't choose either of these 2 people that I've already chosen. And I also can't choose either of their partners because I can't choose the first guy's partner, but I also can't choose the second person's partner, right? So that's a total of 4 people who I can't choose. So when I get here, there are 4 people I can't choose. There are 4 people I can't choose when I get here. So that means that I had 10 to begin with. There are 4 that I can't choose. I've only got 6 who I can choose. And let's do the whole multiplication here. So 8 times 6 is 48, times 10 is 480. All right, so there are going to be 400 different possible arrangements of people, of 3 people rather, from this group of 5 married couples, given that I can't have 2 of them who are married to each other. So hopefully, in going through this, this makes a little bit of sense, slowly but surely. And if you're the type of person who knew the permutations formula, first of all, if you have no idea what I mean when I say permutations formula, that's all right. But just talking to those people who know the permutations formula, well, this is a good example of a problem in which that formula really doesn't help us very much, or we have to make some major modifications to the formula in order to be able to use it, whereas the conceptual approach is much, much clearer. So we're always going to be returning to this slots method for these types of problems. Let's do the next one. So question number 3 from the worksheet. How many 3-digit integers contain 3 different digits? Once again, I'll give you a moment to pause the video and try to do this one on your own. All right, so hopefully you had a moment to pause this video, and of course, if you came to an answer that you're pretty convinced of, well, hopefully it's the right one. And if you really still couldn't figure out where to even begin, that's okay. We'll be going through it together, so you'll know for next time. All right, so once again, let's just think to ourselves, what is this question really asking us? And usually the best way to figure out what a question is asking you is to give yourself some concrete examples. So how many 3-digit integers contain 3 different digits? Well, a 3-digit integer is a number between 100 and 999 inclusive, first of all. So a number like 121 or 356 or 472, any of those numbers, any of these numbers with 3 digits. And we want the number of 3-digit integers that contain exactly 3 different digits. Okay, so that's a bit of a constraint right there. 3 different digits. So, for example, 121 is not going to work because that has 2 of the same digit among its digits. 356, yeah, that works. 472, that works. I don't know, 430, that works as well, etc., etc., etc. So once again, I mean, I could just with pencil and paper start scribbling away and trying to count every single number, every single 3-digit integer that has 3 different digits, and I'd probably get to my answer at some point, but that might not be the quickest approach. So let's do this the same way that we've been doing everything else, right? We're going to approach it using the slots method once again. So this time we're choosing 3 different digits, right? And our question is really similar. I mean, we want to know how many different ways we can arrange these 3 different digits. So let's think about this for a second. We're choosing 1 digit and another digit and another digit. How many different digits are there? So the total number of digits, number of different digits, I could say, different digits, well, 0 through 9, so that makes 10. There are 10 different digits. So there are 10 different digits in total. Now let's think, how many of those 10 digits could I choose for the first slot right here? Well, ordinarily, very reasonably, I'd probably think, oh, I could choose any of those 10 digits for the first slot right there. But we have to consider what that would mean. That would mean I could choose a 9, I could choose a 7, I could choose a 2, a 3, or a 0. Now let's think about that. So a number that starts with 0, like 031, well, that's not a 3-digit integer, right? We're looking for 3-digit integers. Well, that's just 31. That's a 2-digit integer. So in other words, this first number right here, it can't be 0. It can be anything except for 0. Anything except for 0. So that means that there are only 9 options, actually. So I can choose 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay, now that we've gotten that one out of the way, let's take a look at the second, once we get to the second digit. So we want different digits, so we don't want to choose the same one as the first digit. But here, the second digit, well, there's no problem. This can be 0. Of course it can be 0. Here, 301, for example, that's a 3-digit integer right there with 0 as the second digit. So the second digit can be 0 indeed. Okay, so we have 10 digits to choose from. We can choose any of those 10 digits for the second digit, but the only digit that we can't choose is the one that we've already chosen as the first digit right here. So that means that we've got 9 options still. Still got 9 options for that second digit. Okay, now once we get to the last digit, well, first of all, let's think about it. 310, that's a 3-digit integer, so the last digit can be 0. Once again, it can be 0. It can be anything, any of those 10 digits, except we want 3 different digits, so it can't be the first digit that I chose, the second digit that I chose. So that means I can choose any of the 10 digits, except for the one that I've already chosen as the first digit, and the one I've already chosen as the second digit. So that gives me 8 different digits to choose from. All right, hopefully that made sense once again. And let's take a look. So here we've got, well, let's do the multiplication. First of all, 9 times 9, that equals, 9 times 9 equals 81. And 81 times 8, so 80 times 8 is 640, and 1 times 8 is 8, so 648. All right, so I bet you never knew that one before, that there are exactly 648 3-digit integers that contain 3 completely different digits. Amazing the things that you learn while studying for the GMAT exam. Let's continue. Hopefully this is coming together slowly but surely. So, the next topic that we're going to discuss quickly is the difference between these two words, arrangements versus groups. So arrangements versus groups. Now, up until now, the 3 questions that we've done have all been talking about arrangements. They've been asking us for the number of ways in which things can be arranged, whether we're talking about letters or digits or married people. But many questions in combinatorics deal with groups. And let's think about the difference between these two concepts right now. So if I were to return to those letters, first of all, let's take 3 letters, C, D, and A. Okay, C, D, and A, those are 3 different letters. If I rearrange them, I would have C, A, D. If I rearrange them again, I could have D, C, A, and D, A, C, etc., etc. And I would figure out that there are only 6 different arrangements that I can make, but so there's not that many. But let's take a look. So C, D, and C, A, and D. So this one, this first one, and this second one, and this third one, and this fourth one, these are all different arrangements. So these are different arrangements of letters, right? They're arranged. Whoops, I'm not writing very well, but they're arranged in a different way. They're different arrangements. But all four of these belong to the same group of letters. The same group of letters. Right, so they're different arrangements of letters, but at the end of the day, they all contain the same group of letters. Each one of those contains a C, an A, and a D, right? It's the same group of letters. So when we're dealing with things and we're looking for arrangements, what that really means is that the order in which the elements come, right? In this case, letters, the order in which the elements come matters. The order matters, right? This is the big deal of arrangements. The order matters. When we're talking about groups, well, the order doesn't matter. We don't care about the order in which they come. We just care about which elements we have in front of us. So, for example, if you take another look at these letters, well, if we care about the number of arrangements, we're going to say, well, here on this page, we've got four different arrangements written on the page. But if we're looking for the number of groups of letters, well, we've only got one group of letters written on the page because in each of these arrangements, it's just one C, one D, one A. So when a question is asking us for groups, specifically asking us for a situation in which the order does not matter. When a question is asking us for arrangements, it's a situation in which the order does matter. Okay, hopefully that was somewhat clear. Now that's a bit abstract. It may be a bit abstract right now, but let's make it more concrete by looking at some examples. So let's turn now to the next question on the worksheet, which is right here, number 4. How many different groups of 3 different books can be made from a group of 8 different books? All right, so once again, I'll let you pause the video and try it on your own first. Okay, so let's take a look at what we've done. So first of all, how many different groups of 3 different books can be made from a group of 8 different books? So let's once again give ourselves a few concrete examples of what we're talking about. So a group of 8 different books. Let's call them by letter names: A, B, C, D, E, F, G, and H. So we've got 8 different letters here. So one group of 3 of these books would be, well, A, C, D. Another group might be, let's separate that, like, I don't know, E, F, G. Another group, whatever, H, B, C. You get the picture. Now, if I had, however, said HBC and then CHB, well, this doesn't quite work because these contain the same group of letters. So this would be the same group. And we want to know how many groups there are, not how many arrangements. Okay, so how do we deal with this? So first of all, we're choosing 3 books, 3 different books from a group from 8 books. So we'll proceed in the same way that we proceeded with those other problems. Once again, we're choosing 3 books, 1 book, and another book, and another book. right? If we were just looking for the number of arrangements, let's proceed as if we were just looking for the number of arrangements of books. So for the first slot right here, well, there are 8 different books that I could choose. I could choose any of those 8 books. For the second one, once I've chosen the previous book, well, I could choose any of the other books. There's 7 of them. And for the third slot, once I've chosen those first 2 books, I could choose any books that I haven't already chosen, and there are going to be 6 books that I haven't already chosen. Okay, but this number right here, if you think about it, well, it's going to be way too big. If I just multiplied 8 by 7 by 6, that's going to give me a pretty big number, first of all. And that's going to be the number of arrangements of 3 different books. So that would be counting something like HBC and CHB as 2 different arrangements because they're 2 different arrangements of books. But I don't care that they're different arrangements of books. So what I'm going to have to do, and this is where we're going to get a little bit formulaic, what I'm going to have to do is divide. Divide. Right? Nice exclamation points right there. I'm going to have to divide. And what do I divide by? Well, I'm going to divide like this. So I'm going to say here we've got 3 books that we're choosing. We're choosing 3 books. 1, 2, and 3. So right here I'm going to put a 3 because we're choosing 3 books. And under each of the numbers on top, I'm going to put a number on the bottom, and I'm going to count down from 3. 3, 2, and 1. Hopefully that made sense. Might sound a little bit formulaic. We can look at why that works a little bit later on. But this is what we have to do. If we're looking for different groups, we have to divide. And what do we divide by? Well, we always divide by the number of elements that we're choosing. We just count down on the bottom. So here we're choosing 3 elements. So we start with 3, 3, 2, and 1. 3, 2, and 1. We just count down from 3. Okay, so what's really lovely about combinatorics problems is that you can cancel a lot. So I can cancel the 3 and the 2 with the 6. And I'm going to end up with 56 right over here. Aw, excellent. Right. So let's think about that once again for a second. Well, basically, if I'm looking for groups and not arrangements, that means that I'm going to have to divide the number. I'm going to have to divide everything. And how do I divide? Well, I'm going to count the number of slots that I have up here. So here it's 1 slot, 2 slots, 3 slots. Start with 3 and count down from 3 till I get to 1. 3, 2, and 1. If this doesn't fully make sense to you, that's okay. We're going to look at a whole bunch more examples and do questions together. So let's take a look at the next one. Question number 5. If 15 tennis players are in a tournament and each player must play every other player once, how many matches must be played? So once again, I invite you to pause the video and try it out on your own first. Okay, let's take a look at this one together. So it says we've got 15 tennis players. So I'll write that down. 15 players. Each player must play every other player once. So let's think. So each player must play every other player once. How many matches must be played? So here are the number of matches. Now, sometimes in a question, it doesn't actually specify that you're looking for groups. But if you think about it, a match is just a group of 2 players. Right, a group of 2 players. If I have player A playing player B, well, it doesn't matter if I choose player A before player B or if I choose player B before player A, it's still going to be the same group of two players. It's still going to be the same match. So here I'm looking for groups of two. So I'm going to put down two slots. I'm choosing one player and another player. Now, I'm dealing with groups here, groups of two. So that means I've got to divide. And what am I going to divide by? Well, I've got two slots here. So I'm going to put 2 times 1 right down there. And on top, I've just got to do everything that I would have done normally if I were looking for arrangements in those first few problems that we did. So in that first spot, I can choose any of those 15 players. So there are 15 possibilities. And then the second spot, once I've chosen that first player, well, I can choose anybody who's left. There are 14 players left. Okay, and do my nice cancellation here. Times 7. So here we have 15 times 7, or 3 times 5 times 7, or 3 times 35, which is 105. Okay, so hopefully this is coming together a bit for you. Let's take a look at the next problem right now. So problem number 6. From a group of 6 professors and 8 students, how many committees can be formed containing exactly 2 professors and 3 students? So once again, I recommend that you pause the video and try to tackle this one on your own first. Okay, now let's look at this one together. So first of all, we've got a group of 6 professors and 8 students. So let's write that down right up here. So we've got 6 professors and 8 students. Write it like that. And here we want to choose 2 of the professors, so 2 of these guys, and 3 of the students, so 3 of the students. Now what's really important, whenever you have something in which you're choosing 2 of a certain group and 3 of another group, or some number from a certain group and some other number from another group, is that we must keep the different populations separate. Okay, what's a population? Well, the population is kind of the total number of people that we're choosing from. So we'd say that these are the two, what we call populations. So there's the population of students and there's the population of professors. And whenever we're dealing with a combinatorics problem, we have to keep, I'm going to write this, keep populations separate. Keep the population separate. Okay, so that means I'm going to be multiplying one thing here. I'm going to choose my group of professors, and I'm going to choose my group of 3 students. So here I'm going to choose 2 professors. So I'm choosing one professor and another professor. Here I'm choosing 3 students, one student and another student and another student. In each case, I'm looking for groups of students. If you think about it, here we're talking about how many committees can be formed. Well, committees, a committee, it doesn't matter who I chose first and who I chose second and who I chose third. For a committee, it just matters that I chose this person, and this person, right? It doesn't, the order in which I choose the people for a committee doesn't change the particular committee that I formed. So here we're looking for the group, so we need to divide, right? So groups, remember, groups equals divide. Okay, so what do we divide by? Well, we're keeping the populations separate once again. So on this side, we're going to divide by, for the professors, we're choosing 2 of them, so we're going to divide by 2 times 1. For the students, we're choosing 3 of them, so we're going to divide by 3 times 2 and then times 1. And then finally, we'll fill in everything else. We had 6 professors, so that means that for the first one, I can choose any of the 6. For the second one, I can choose any of the 5 that are remaining. We have 8 students in all, which means that for the first student, I can choose any of those 8 students. For the second one, any of the 7 remaining. And then for the third one, any of the 6 that are remaining after that. Okay, so now let's do all the cancellation. We can cancel the 3 and the 2 with the 6. We can cancel the 2 with the 6 right here. So that gives us 3. So here we have 3 times 5 times 8 times 7. Let's say that this is going to be, so 5 times 8 is 40. It's getting a little messy. 5 times 8 is 40, and 7 times 3 is 21. So this really comes down to 40 times 21. 40 times 20, of course, is 800, and 40 times 1 is 40. So we have 840. 840 is going to be our answer. All right, so a couple takeaways there. Keep the populations separate if there are 2 populations. That was the only thing that we really added here. And remember, they don't always say groups. If they're looking for groups, they might say something like committees or matches or pairs or something that really implies that the order in which we're choosing the people doesn't affect the number of things that we're counting. All right, let's continue. Let's continue. Whoops, that's not the one that I wanted. Let's go this way to number 7. So question number 7. From a group of 6 chemists and 4 biologists, how many 3-person committees can be formed containing at least 1 biologist? Okay, so once again, I'll let you try to work this one out on your own first. Okay, so let's take a look at this one together. So, similar to the previous problem, number 6, we've got 2 separate groups. We've got 6 chemists, and we've got 4 biologists. So 2 separate populations. 6 chemists and 4 biologists. So how many 3-person committees can be formed containing at least 1 biologist? The only thing that we don't have is we don't know how many chemists are going to be in each committee and how many biologists are going to be in each committee. All right, so in each of the previous problems, we've known exactly how many people were going to be in one and exactly how many people were going to be in the other. Well, we don't quite have that situation here. But we do know that we need at least 1 biologist. We need at least 1 biologist. So let's think of our options. Well, if we have at least 1 biologist, we could have 2 chemists, so a chemist, and 1 biologist. That's one possibility. Or we have 1 chemist and 2 biologists. That's another possibility. Or, finally, we can have 3 biologists. That's another possibility. So, if you think about it, we've either got this, or we've got this, or, once again, we've got this. So those are 3 different possibilities. So, if you remember back to the beginning of the lesson, the workshop, or has to do with the addition principle. So we're going to think, okay, how many different groups contain 2 chemists and 1 biologist, plus the number of different groups that contain 1 chemist and 2 biologists, plus the number of different groups that contain 3 biologists. Okay, so So let's do this together. So if we're taking the number of groups that contain 2 chemists and 1 biologist, right, we've got to keep our population separate. So that's going to be 2 chemists, 1 chemist and another chemist, and 1 biologist. Now, here once again, it's committees. We're looking for the number of different, oh, didn't mean to cross it out, the number of different committees. So the order doesn't matter, so we're going to have to divide. So we're dividing by 2 times 1 here, and by 1 here, even though it's kind of trivial. Okay, so remember we had 6 chemists to choose from. So for the first chemist that I choose, I've got 6 possibilities. The second one, I've got 5. We had 4 biologists to choose from, so I can choose any of those 4 biologists. Okay, let's take a look at the second. So remember, that's this first option right here. Let's take a look at the second option. Here we're choosing 1 chemist and 2 biologists. So 1 chemist and 2 biologists. That's 1 biologist and another biologist. Once again, I'm going to divide. So here, for the chemist, I'm dividing by 1. For the biologist, since I'm choosing 2 of them, I'm going to divide by 2 times 1. Okay, and I could choose any of the 6 chemists to begin with. And for the biologists, the first biologist I choose, I've got 4 options. Then I've only got 3 left. So that's for this second possibility. And then finally, if I'm just choosing 3 biologists, that's 1 biologist and another biologist and another. The order doesn't matter, so I'll divide by 3 times 2 times 1. I've got 4 possibilities for the first biologist, 3 for the second, and 2 for the last one. Okay. Now remember, so first of all, this is for this last option. And of course, it's either this, so it's either the first one or big plus sign, the second one or the third one, big plus sign. So I'm going to take each one of these answers and add them together. So let's do some cancellation. We can cancel the 2 with the 4, and we've got 30 times 2, which is 60. We can cancel the 2 with the 4 here, and we've got 6 times 6, which is 36. And here we can cancel the 3 with the 3 and the 2 with the 2, so we end up with just 4. So remember, it's either this, either 60, or 36, or 4. So either 60, or 36, or 4. So we're adding them all together to get a nice round 100. So that's the answer to this problem, 100 different options. Okay, hopefully this is becoming clear just by the process of doing it over and over and over again. We're going to now come to the last question on the worksheet. Now this question really throws everything together in one question. So it's going to be a good review question for everything. And then after that review question, I'll have you take a look at some practice problems, which you can also find in the PDF at the bottom of the screen. So let's take a look at this last question, number 8. From a group of 5 married couples, so those same 5 married couples that we met in question number 2, how many committees of 4 or 5 people can be formed if no 2 people on the committee may be married to each other? All right, once again, and I really highly recommend it for this problem at least, try this one on your own, pause the video, and see how you do. Okay, so hopefully this problem allowed you to really put everything together all at once. It is a great review problem for everything that we've looked at today. So from a group of 5 married couples, how many committees of 4 or 5 people can be formed if no 2 people on the committee may be married to each other? So we've got the same constraint that we had in question number 2. We can't have 2 people that are married on either of the committees. Here we're dealing with committees. Committees, once again, committees. So that means groups, which means the order doesn't matter, does not matter. And here we're choosing 4 or 5 people, right? 4 or 5 people. So let's think about what that means. Well, we're going to count the number of committees of 4 people for which this constraint would work. So we're choosing one person and another person and another and another. Oops, let me close that. So 4 people plus, right, or so plus the number of committees of 5 people. One person and another and another and another and then another, right? Okay. So we really put everything together. Now, as we said before, groups, we're dealing with groups here. We're looking for the number of different groups, and that means we've got to divide. Okay, so what do we divide by? Well, here we're choosing 4 different people, so we'll divide by 4 times 3, 2, and 1. And the second half, we're choosing 5 different people, so we'll divide by 5, 4, 3, 2, and 1. Perfect. Now, let's think about our constraints. So once again, we've got 5 married couples, which means that we have 10 people in all. So for the first person that I choose here, I can choose any of the 10 people. The second person, I can choose anybody except for the first person. And as we saw in question number 2, we can choose anybody except for the first person and that first person's partner. So there are only 8 people that I can choose for the second slot. Once I get to the third slot, I've only got 6 remaining. And once I get to the fourth slot, I've only got 4. On this side, it's going to be a similar thing. I've got 10 people for the first slot, 8 people for the next one, 6 for the next one, 4, and 2 for the last slot for the same reason. Okay, so if you got that, well done. Bravo. This really puts everything together. Now let's just do the calculation and let's see what we end up with. So let's cancel the 3 and the 2 with the 6 over here, and we can cancel the 4 over there. And on this side, what can we cancel? Well, we can cancel the 4 with the 4, the 2 with the 2, the 3 with the 6 becomes a 2, and the 5 with the 10 becomes a 2. So here we've got 10 times 8, and that's it, so 80. And here we've got 2 times 8 times 2, which is 8 times 4, or 32. 80 plus 32 is 112. Perfect. So there are 112. All right, so this worksheet has really taken you through all of the basic things that we need to know to approach GMAT permutations and combinations questions. We went through situations in which we had arrangements. That's what we cared about. We also went through some situations in which we had groups, and that's what we cared about. Now, let me just take a quick moment to go down, and let's review. Let's make a big review of the stuff that we saw. And then we'll take a look at some practice problems. Review. Okay, so number 1. What did we look at? We looked at the multiplication principle, or multiplication rule, and the addition rule. Addition rules. So multiplication rule, multiply. Addition rule, add. And you use the multiplication rule when you have the word and, when you're doing one thing and another thing. And the addition rule when you have the word or, when you're doing one thing or another thing. Right? Very important. Next, we went through the slots method. The slots method. And it basically, what does it look like? Well, depending on the number of things that you're choosing, one thing times another times another. And with each thing, we kind of say to ourselves, okay, how many options do I have for this first slot? How many options do I have for the second? And so forth. Next, we talked about the difference between arrangements and groups. Whoops, arrangements versus groups. Arrangements, the order matters. Groups, order does not matter. Doesn't matter. And with arrangements, let's draw a line between these. Arrangements don't divide, right? If the order matters, don't divide. If the order, of course, doesn't matter, then you must divide. Right? If the order matters, don't divide. If the order doesn't matter, then divide. Okay, and what do we divide by? Well, so what do we divide by? So with groups, once again, if we're choosing one thing and another thing and another thing and another thing, for things, we're going to count the number of things that we're choosing, put that number right there, and count down to 1. So 4, 3, 2, and 1. There you go. Next consideration, of course, is keep populations separate. Keep populations separate. Perfect. Keep populations separate. And I think that covers pretty much everything that we saw today. So once again, there's a PDF of the practice problems just at the bottom. So I'd like you to do there are 6 practice problems. And once you've done them, you can pause the video for now. Once you've done them, you can come back and take a look. We're going to go over those practice problems together. So enjoy. All right, so if you've done those practice problems, hopefully they all came together. None of those were particularly easy problems, so you can certainly congratulate yourself on that. Let's go through them together one by one. So question number 1. Question number 1 reads, in how many ways can a group of 6 people, of whom 3 are men and 3 are women, be arranged in a row of 6 seats if no 2 people of the same gender may be seated next to one another, or next to each other, I suppose it should be. Okay, so how many ways can a group of 6 people, of whom 3 are men and 3 are women, be arranged in a row of 6 seats if no 2 people of the same gender may be seated next to each other? Well, let's take a look at some of our different. Let's give ourselves an example first. So if I have 6 seats, 1, 2, 3, 4, 5, and 6. Well, if I started with a man, put an M, then I'd have to have a woman here, then a man, then a woman, then a man, then a woman. And similarly, if I started with a woman, then I'd have to have a man, a woman, a man, a woman, and a man. So it really depends on who I start with in a certain way. Well, but at the same time, let's approach it like we have approached any of our other combinations problems from the worksheet. So first of all, I'll put in the slots. I'm choosing one person and another person and another person and another person and another and another. Here we're looking for the number of arrangements. It asks us specifically in how many different ways can they be arranged. And remember, if we're looking for arrangements, don't divide. Arrangements don't divide. Don't divide. Okay. So, for the first person that I choose, well, how many people could I choose? Well, I could choose any of those 6 people. Really, I could choose any one. It doesn't really matter when I choose that first person. There are no constraints against that person. Once I get to the second slot, though, let's think about how many different people I can choose now. Well, if this first person I chose was a man, then I could choose any of the 3 women that are remaining for the second slot. And if the first person I chose was a woman, for the second slot I could choose any of the 3 men. So in any case, I've only got 3 people who I can choose for the second slot. Once I get to the third slot, well, I need to choose somebody who's of the same gender as the first slot. Well, so if it's a man, there are only 2 men left. And if it was a woman, if the first person I chose was a woman, there are only 2 women left. So I've got 2 people in either case remaining. Finally, once I get here to the fourth slot, I can choose anybody of the same gender as the second person who I chose. Well, there are going to be 2 people remaining there. And then 1 person and 1 person. Multiply this all together. 3 times 2 times 2 is 12 times 6 is 72. So our answer here is going to be answer choice D, 72. Hopefully that made sense to you. Let's take a look at the next problem now. So here it says, from a group of 8 junior employees and 4 senior employees, how many different teams of 4 can be formed if each team must have a greater number of junior than senior employees? Okay, so let's think about this by giving ourselves first some examples. First of all, we've got 2 different populations. 2 populations. Whoops, populations. 2 populations. We've got 8 juniors and 4 seniors. So we're going to have to keep those populations separate. And let's think of our different options. So we have to have a greater number of junior than senior employees, and we're choosing 4 people. So that means that we could have, for example, 3 junior employees and 1 senior employee. That's one option. Are there any other options that would have a greater number of juniors than seniors? Well, yeah, actually. I could have 4 junior employees and absolutely no senior employees. That's another option. So it's either the first one or the second option. And remember, or means I'm adding them together. Now, if you thought, well, can't I just have 2 juniors and 2 seniors? That doesn't quite satisfy the condition in the problem, because it says each team must have a greater number of junior than senior employees. So we can't have the same number of junior and senior employees. Okay, now all we need to do is do the math. So first we're choosing 3 junior employees and 1 senior employee. So that's 1 junior and another and another and 1 senior employee. Here we're talking about teams. Teams, you know, if you think about it, a team, right? A team is a group of people, right? Groups we don't divide. Groups we divide. So we're going to have to divide this. So we're going to divide here by 3 times 2 times 1, and over here by 1. Okay, how many could we choose for the first one? Well, we could choose any of the 8. For the second one, it's going to be any of the 7 left. And the third one is going to be 6. And for the senior employees, well, we could choose any of the 4. Right? So that's this first option right here, where we have 3 juniors and 1 senior. Let's take a look at the options where we have 4 juniors. So if we have 4 junior employees, that's 1 junior and another and another and another. Right? 4 junior employees. The order doesn't matter, so we're going to have to divide by 4, 3, 2, and 1. And on top, well, for the first slot, we can choose any of the 8 junior employees. For the second one, any of the 7 remaining. For the third one, any of the 6 remaining after him, and then 5. Okay, and then finally, we're going to take these two and add them together, right? We're going to add them together because it's either this one or it's this one. Okay. So yeah, so this one goes with the 4 juniors and no senior employees. Okay, so let's do some cancellations. So 3, 2, and 6. So here we have 56 times 4. Now 50 times 4 is 200. 6 times 4 is 24. So this whole thing is going to multiply to 224. And here we have, well, let's do some cancellation once again. The 3 and the 2 can go with the 6. We can get rid of the 4 with the 8. It becomes a 2. And so here we're going to have 2 times 5 times 7. Right? 2 times 5 is 10, times 7 is 70. So at the bottom, we're going to have 224 plus 70, which brings us all the way to 294. So that is our answer right there, 294. Very well done if you got that one right. Now let's take a look at the next problem. So let's go over. Problem number 3. So in an international student exchange program, 5 different countries are each represented by 5 students. Okay. How many different 5-person committees can be formed from the students at the exchange program if no committee is to have 2 people representing the same country? All right. So let's think about this step by step. So first of all, it seems we have 5 different countries. Each of those countries is represented by 5 students. So that seems to imply that there are going to be 25 students. So 25 students in all. 25 students in total. And we can't have 2 students on this committee who are representing the same country. So that's an interesting constraint right there. Now we're also choosing 4-person committees. It says 4-person committees. Committees are groups, right? So that means groups. And of course that means divide. Groups, that means divide. All right, so let's take a look. So we're choosing 1 person and another person and another person and another person so far. We're going to divide. So we're choosing 4 people. So we have to divide by 4, 3, 2, and 1, as usual. Now on top, for the first person that we choose, we could choose any of those 25 students. Once we get to the second person, we can choose any of the 25 students except for the 4 other students who are representing the same country as the first student that we chose. So once we choose a student, we've got to get rid of all the people that are also representing that student's country. So now we're going to have only 20 students for the second option. Next, well, once again, we can choose anybody except for the first 2 students and any of the other people from their countries. So that represents 10 students that we can't choose. So we've only got 15 remaining for the third person. And then for the fourth one, well, we've only got 10 after that. Okay, let's do the math on this one a little bit. So we'll do some cancellation. We can cancel the 20 with the 4, it becomes a 5. We can cancel the 15 with the 3, it becomes a 5 as well. And we can cancel the 10 with the 2, and it becomes a 5. So here we have 25 times 5 times 5 times 5. And let's take a quick look at the answer choices. So sometimes before you do a big calculation, you want to always look at your answer choices to see if you have to actually do that calculation. Now what you'll notice is that some of the answer choices have exponents. And in fact, that includes the one that we're looking for. Because after all, 25, right? 25 is just 5 times 5. So this is 5 times 5 times 5 times 5 times 5, or 5 to the power of 5. Right, that's going to be our answer, which is answer choice C. Now, very quickly, you might have looked at D and E and noticed these exclamation points in the answers, right? Well, the exclamation points, if you've never seen that before, so that's something that we call a factorial. And all it means something that we've already been dealing with. It means taking a number, so like 4 factorial, means you take 4 and you multiply it by every integer less than 4 until you get to 1. So 4 times 3 times 2 times 1. If we had 6 factorial, that would just be 6 times 5 times 4 times 3 times 2 times 1. Right? 4 times 3 times 2 times 1. That's 4 times 6, or 24. And then 6 times 5 times 4 times 3 times 2 times 1. Well, that's 30 times 24. 30 times 20 is 600, and 30 times 4 is 120. So that's going to be 720. Right? So factorials, they kind of look funny, especially if we've never seen them before, but we've already kind of been dealing with that concept when we've been, dividing by descending integers or writing descending integers on top. Right? But in this problem, the factorials were not the way to go for the answer choices. The correct answer is answer choice C. All right, so hopefully that went well. Let's take a look at the next problem. Problem number 4. It says a small country will generate identity codes for some of its citizens. Each code will contain 4 or 5 characters drawn from the 26 letters of the alphabet and the 5 least digits. Okay, what is the maximum number of people who can be uniquely designated under such a system? All right, when it asks us the maximum number of people, well, the maximum number of people is going to be the maximum number of, it's going to be the number of different codes. Before you have to have 2 people that have the same code if there's more people than the number of different codes. Let's take a look at this. So first of all, we want this to generate identity codes. Now a code is a situation in which the order matters. The order matters. If you think about it, right, if we have a code, I don't know, 3, 2, 1, well, that's a different code from 2, 3, 1, right? And what makes these different is even though they've got the same group of letters, those letters come in a different order. So these would be different codes right here, right? So you can think of it there. So the order matters, so we're not going to divide, right? Order matters, don't, write it right up here again, don't divide. Whoops. If the order matters, don't divide. Very well. Okay. So let me get rid of that. Whoops. Oh dear. Okay, if the order matters, don't divide. So it says each code will contain 4 or 5 characters drawn from the 26 letters of the alphabet and the 5 least digits. So we've got, let's think about the population. The population here, well, the population is going to be the 26 letters of the alphabet and the 5 least digits. So that's 31 different elements, we can say, or 31 different things. Right, so the population is 31. All right, now let's get to the work of solving this problem. We want a code that contains 4 or 5, so it's or 5, which means that we're going to basically figure out the number of codes that contain 4 digits, one and another and another and another. Whoops. And add it to the number that contain 5 digits, 1, 2, 3, 4, and 5. Right. Okay, so the number that contain 4 digits, well, we've got 31 to choose from for the first digit. Once we've chosen that digit, well, it doesn't say that we can't repeat the same digit, right? So we could still choose any of the 31. Once we've chosen that one, we could still choose any of the 31. And we could still choose any of the 31. The same would go for this side, right? It doesn't say that we can't repeat the digits. All right, so this whole thing here is going to be 31 to the fourth, and this whole thing here is going to be 31 to the power of 5. All right, now you look at your answer choices and you say to yourself, oh, I don't see it. I mean, answer choice C is very close, which is true, but close is unfortunately not going to cut it for the GMAT, right? Close is still not close enough. All right, so we've got to figure this out. So we've got 31 to the fourth plus 31 to the fifth. Now, whenever you're dealing with two what we call terms in algebra, we would always try to find a common factor between the terms. So let's think. Let's give ourselves an example. If we have x to the third plus x to the fourth, we could always rewrite this as x to the third times 1 plus x. Because when we distribute this, x to the third times 1, well, that equals x to the third. And x to the third times x, well, that equals x to the fourth. Same thing here. We can say that this is going to equal 31 to the power of 4 times 1 plus 31, right? Because 31 to the power of 4 equals 31 to the power of 4, and 31 to the power of 4 times 31 equals 31 to the power of 5. So this whole thing equals 31 to the fourth times 32, which is our answer. And indeed, it's answer choice D. So if you got that one right, you can pat yourself on the back. Very, very well done. All right, let's move on to the next question, and let's see how you do. Question number 5. A row of 7 chairs must be filled by 7 different students from a group of 4 graduate and 5 undergraduate students. Okay. If each seat must be filled with either an undergraduate or a graduate student, how many different arrangements of students for the 7 seats are possible? All right, let's just quickly draw the 7 seats. So 1, 2, 3, 4, 5, 6, and 7. This is similar to the first problem in some ways. Now here it's saying we have a group of 4 graduate and 5 undergraduate, but it really, in each seat, it doesn't matter whether it's a graduate student who's sitting in the seat or an undergraduate student who's sitting in the seat. So what we've really got is just a population of 9 students. Population of 9 students. It doesn't, in any case, it really doesn't matter if it's a graduate or an undergraduate student. Finally, we're looking for arrangements, right? So I've said this quite a lot, but don't divide. Don't divide. If we're looking for arrangements, don't divide. Okay, so let's see, we've got 9 students in all. So that means that we can choose any of those 9 students for the first seat, and any of the 8 remaining for the second, and any of the 7 remaining for the third, and any of the 6, so on and so forth. Okay, now once we've done this, let's take a look. This seems like it's going to be a pretty long calculation to do, so let's take a look, as usual, at our answer choices and see how much of this calculation we really have to do so far. Okay, well, looking at this already, I can say, well, it's definitely going to be greater than 6. So we can eliminate 6. Similarly, it's going to be greater than 36, so we can eliminate that. Now let's do some of this calculation and see if we can eliminate anything else. So 9 times 8 is 72, and we'll multiply that by 7. So 72 times 7, 7 times 7 is 490. 7 times 2 is 14. So that's going to be 504 so far. So that's 504. 490 plus 14, yeah, makes sense, 504. And then we multiply this one by 6. Okay, well, already I can see that if I multiply this 504 by 6, I'm going to be way above 720. Okay, so that seems apparent. Now, 500 times 6 is going to be 3,000, and 4 times 6 is going to be 24. So this is going to give me 3,024, this multiplication here, which I'm then going to multiply by 5, right? Then I'm multiplying it by 5. Now, if I multiply this number by 5, I've already got something that's bigger than 5,040, so I can eliminate that. And I don't really need to go go any further to know that, okay, this is going to be a big number. And indeed, it is going to be a big number. It's going to be 181,440, or answer choice E, right? So I didn't need to go the whole way of doing that calculation. I could just sort of strategically eliminate answer choices as I went along. Okay, to wrap up, let's look at the last problem. And if everything has gone well so far, then you're an absolute pro at combinatorics. So question number 6. It says the 16 players in a chess tournament must each play every other player in the first round of the tournament. Only half of the 16 players will play in the second round, each player playing every other player, and only half of them will play in the next round, a pattern that will continue until only one winner is left. So finally, how many chess games will be played in the tournament? Okay, so here we're going to try to have to figure it out the number of different rounds. So round 1, let's say round 1, we're going to have 16 players. 16 players. Round 2 says each round half of the previous number of players are left, so it's only going to be 8 players in round 2. Round 3, well, only half of them are left, so 4 players. Round 4, let's take a look. Round 4 then, could be 2 players left, and then that's it, because the winner is going to be the winner. There's going to be no more games. All right, so in each case, we're looking for games, number of games. Well, game is just the same thing, basically, as a group of 2 players. So we can say group of 2. Not 21, I don't know why I wrote that. Group of 2. Okay, groups, once again, we have to divide. So groups, divide. All right, so here, round 1, we're going to have 16 times 15 divided by 2 times 1. Round 2, right, that's for round 1. Round 2, sorry, I should have followed the slots method. One person and another. We're going to have 8 and 7 divided by 2 and 1. Round 3, one person and another person. We're going to have 4 times 3 divided by 2 times 1. And then round 4, we're going to have, once again, 2 players. 2 times 1 divided by 2 times 1. All right, so that will tell me exactly how many games are in each round. And here we can cancel this out. So we cancel the 16 with the 2 to get 8 times 15. So 8 times 10 is 80. 8 times 5 is 40. So that's going to be 120 games. We can cancel the 2 here with the 8. Get 4. 4 times 7 is 28. Cancel the 2 here with the 4. 2 times 3 is 6. And then we can cancel everything here and get 1. So here it's going to be 120 plus 28 plus 6 plus the final game. And we can add all of these together and find out that it is 155. So, which is answer choice E. All right. So, thanks for making your way all the way to the end of this video and to the end of combinatorics. It's been a fun ride. I hope you've really enjoyed it. And really, if you're comfortable with the stuff that we've done today, and even if you're not, but you put in the effort to really become comfortable with it by redoing the problems that we saw or rewatching parts of the video that you need to take another look at, you will be an absolute combinatorics pro for the GMAT exam. I assure you. Now, there are other topics much lesser, far less seen on the GMAT that do come up in combinatorics, and I hope to kind of throw them into a video at a later date. But this really goes through the basic conceptual underpinnings of combinatorics and the stuff that you really absolutely essentially have to know for the GMAT. So I hope you really enjoyed that. Once again, down at the bottom, you can click on the link and you'll get a link to my website, which is EuroGMAT.com. You can also download the 2 PDF files of number 1, the worksheet for this lesson, for this workshop, and number 2, the practice problems. And also on my website, you can get more practice problems that deal with each of these, or that deal with all the topics that we've seen today. So thanks a lot for listening. And if you have more questions, you can always write to me, contact me through the website. I try to respond to everybody's questions. So thanks a lot. Cheers.